So I apologize for the interruption. So let me resume back. So we assume the length here 1, 2, 3, 4, 5. We have actually 5 characters as a length. Okay, and so we said that when we was explaining I equal 1, so and we said the result now is having t. So this condition is make sure that we never exceed the length of the whole input. So we should never exceed 5. So the length here, the length is actually 5 characters. Okay, so the start index, which is in this case 2, and I is equal 1, so this is 3, and the length is equal 5. So we need to make sure whatever we have here is always less than 5, which is the length. So we should never exceed that, the total length of the input. Okay, so okay, so now since we are having I equal 1, so let's have a look. So when start index equal 2 and we add I, which is equal 1, so it becomes 3. So we will take this t again with us. We will add it to the result. So now the result is having 2 t's. Okay, and then let's have a look again. We will see that okay, I is incremented to become 2, and when it is become 2, so edit I is less than the length actually, which is this one. Okay, so is it 2 is less than 2? It's actually no. So this condition fails. So if it fails, it means that the for loop will stop. So I said that I want to start at start index at 2. I also wanted the length to become 2. So it means that I want to start at 2 and I want only get 2 characters. So I got them here. And then since this condition will stop the for loop, so we will exit and then we return back here t and t. Okay, so this is just an example of how this slice string works. So I made this slice string because I didn't want to use anything that is outside the scope of the syllabus, since I am not aware if this was explained in the class or not. So that's why I use that. So actually there is functions that is called substring. Okay, this is part of the string library, but I didn't use it because I was not sure if this is actually you take it in the class or not. But in the syllabus, it's not clear if you ever take it or not. It's not mentioned at all. So that's why I try to stick to the basic solution for that. Now have a look here. Let's move. So this strand similarity, we already have it from previous question 3. So it is used there in this best strand match. So what we're going to do here, first, I told you before, this integer is a casting because this length return size t data type, which is will cause a problem in the canvas. So this is not acceptable in the canvas, but acceptable in normal programming like Visual Studio, and even on this cloud platform is accepted, totally no problem. If I remove that, it will work. But anyhow, so I'm storing the length of the input and target both here and here. And now I am comparing. So if the target is bigger than the length of the target is bigger than the length of the input, I will off. I will not do anything. I will return -1. I will just print that before I go. This is part of the requirement, and also on the error handling conditions. So this is considered like an error. So I will declare 2 variables, best score and best index. So as we said, we need to print the best score and we need to return the best index. So this will return and this we will print. And then we will start looking here. So we'll do also a for loop. Okay, the for loop actually okay, so first of all we will try to slice the string. So we will slice the input based on the target length. So if the target length is normally the target is either equal to or less than the input. So let's assume that this target length is 3. So it means that we need to actually slice the input starting from I here, so that we cut the input. So imagine that, let me imagine that this is actually the input. And let us imagine that we have T, T, U as a target. So we will find that, okay, we're starting at position 0. This is 0, 1, 2, 3, 4, 5. We're starting at 0. And then we would like actually to slice. We want to do comparison between two equal strings. So we have to cut the input. So we pass this whole input, and we will cut it according to the length of the target. So the length of the target is 3 characters. That's why we pass it here in the slicing string that we know. And we will start from 0 because I here equals 0. So we'll start from 0. So when we are here, so we will cut that, and we will return only, we will get ACT according to the same length of the target. So now we will compare this string to actually the target. So we will compare 3 characters to 3 characters, and we will check the score. Okay, so what we are trying to do is actually we will try to get the best score. So we try to compare the target with every possible combination inside this input string. Okay, so again, every time we execute the loop, we will actually cut the input with the exact character, and then we do comparison. This comparison actually is done in the strand similarity, which is part of question 3. So we will get a score, and then we are going to store the best score. So if the current score that's coming here is bigger than the best score, which is in this case, we start from 0. So definitely any score that comes here will tell us, oh, okay, so there is a matching. Actually, in this case, A and C, C and T, T and U, there's no match. So you will find that this score is 0. So definitely your current score, which is 0 that you get here, is not bigger than this. So you will store nothing. Okay, so maybe if you move, so we increment the I. So I now become 1, and then we start to slice again, but using I equal 1. So when we slice again, we will find that, oh, we are no longer starting from here. We're starting to cut 3 characters, but from this place. So, and then we store them in input section, and then we pass them to the strand similarity. So when we pass them to the strand similarity, then we get a score. So we find the C matching the C, the T matching the T, and the T is not matching the U, but it means that 2 characters out of 3 is matching. So you will find here maybe 0.66 as a result. So if you have the score 0.66, so this score is bigger than 0. So definitely we will store this, our current score, 0.66, inside the best score. Okay, and we also store the I, because I now it is marking that this position here is actually having a good score, at least at the moment we discover that it is one of the best scores. And then we increment the I to become 2, and we start to slice again. So when we slice again, so let me put here that this best index have 1 at the moment, because this is the best, marking the best score. Okay, now we will start to slice from this index 2. So index 2 will cut 3 characters, and we will store them in input section, and then we pass them to the strand similarity, which will do the comparison, T and C, T and T, and T and U. So only match 1/3. So definitely that was 0.33. So this score will be 0.33. Is it better than the best score? Definitely no. So we will keep the best score. So this is this portion is to actually keep for us and store for us the best score. So we do not use the score that is coming out from here does not replace the best score. So we always keeping the best score protected by this if statement. Okay. So okay, like we said, the best score occurs at position 1. So again, this will I will be incremented to 3. So again, when we increment it to 3, it means that we start to cut the last 3 characters. Okay, so when we start to cut and then we compare them, C and T doesn't match, T and T match, U and U match. So that is 0.66 also. Okay, but we are going to compare and see if the current score is bigger than the current one stored. So 0.66 is not bigger than 0.66, it's the same. So this means that we will stick to the first one because it's already stored there. So the point here that you cannot increment the I more than that. Why? Because if you increment I to become 4, so the point here, if the input length is equal 1, 2, 3, 4, 5, 6, so it's 6 characters, and this is 3 characters. Okay, so if you subtract 6 minus 3, so it's equals 3. This is the stopping condition here. So I is less than or equal this value. So when it is equals 3, it is accepted. Once we start to increment I equal 4, so this will be bigger than these two. So it means that we are not able to take another 3 characters and compare it to our input. We already reach the end of our input input strand that we are able to cut. So this is the last position that we are able to use to do this slicing, you know, because we are not able to come here and say we want to slice 3, because that will exceed the length of the input. So we cannot do that. So again, input length minus target length, and then you reach a value, and then you say this condition so that you stop your loop here. So okay, now we will print out the best similarity scores. The problem is in the canvas, if you do a single error, if you do this, if this best is actually B small, he will not accept it. If you forget the colon, he will give you an error. So even this space also will give you an error. Every single character here must exactly match what he write to you in the sample run. Every question will have a sample run, so you always need to match the sample run. Okay, now I would say, and we will print the best score, and after that we will return the best index, which is 1 in this case. Okay, so this is assertion. I can pass you the code, you just need to ask for that if you didn't take a copy from the code. So this is assertion. So every time I pass it an input, I will check if the output actually match this input. And here, this is checking for the slicing, if it really cut according to our specification, if it's really working fine or not. And this is asserting. So we will pass it input and target, and then we will check if the best index is returned correctly or not. So you can take the sample run that is provided in the table in your instruction book, and then you compare both and to the output that is given in the table. And if it matches, it means that your function is working properly, but it still doesn't mean that it will work in the canvas. Sometimes it's a bit tricky in the canvas, because in the canvas it checks for a different situations and inputs than the sample run. It provides some tests that actually can really make trouble to your code, but not in question 4. So let us have a look at question 5. So question 5 is a bit tricky. I would say the code is not tricky, but here is a bit tricky. So the question itself. So we have to actually check for something called substitution, insertion, and deletion. And yeah, there is many conditions that we need to really check. So okay, we have again this identify mutations. We have input and we have output. We will return nothing from this function. We will only do printing. So this function compared to DNA sequences to identify all types of mutations, all type of changes that is done. It aligns the sequence based on the best possible match. So this is the based on the best score. So we will align the input and the target based on the method that we just finished in question 4, okay, which is giving us the best score. It will be telling us the best score, and it will be telling us also the best aligning index that we can start at, and we will start to compare character by character and print out the mutation as they are detected. So so let me see here. So we may assume that the input and target are both valid, so we don't need to check anything like that. If no mutations are found, the functions will output no mutations found. And this specifically actually caused a problem. I believe it caused a problem on question 9, maybe not here. So just because of a string that need to be printed only. So this is sometimes most of the problems with the canvas is like that. He checked for extra checks. So as you can see, I believe so this is the input and this is the target. So we try to align based on the best score. We try to align them according to the best match possible. And then we start to say that since the input have A and C and the target does not have them, so it means that something was deleted from the target strand. So A and C is actually marked as being deleted from the target. Okay, that's one thing. And then you look at here, T match T, so there's no problem. T match T, no problem. G and C does not match, and G and A does not match. So substitution means that G was changed to A. Okay, so substitution, this happened at position. I'm not sure why he said position 4. He said position 4, which is it is true because human are counting from 1, but the computer is counting from 0. So that's why he said position 4. And also you can see here G is not matching with C. So he's saying that substitution also happened at position 6. So G was substitute is changed to C here. And then if you see the T, so he will also say that the T was deleted. Okay, he does not show you here an example of an insertion. Okay, because as you see, this target strand is actually less less in size than the input. That's why it's only either deletion or substitution. So we will see an example of actually insertion. Okay, and when this will happen. So if you see that the input is actually if the input is actually less in size than the target, so then only then you will see the insertion. So it means that when we start to match, so we will see that okay, G G G. So we are matching at maybe okay 0 1 at position 2. This is the index 2. We are matching both the target and this is the target and this is the input, and it means that T and A was inserted. Actually, it is something that is not present in the input, but we have it in the target. So that's why we say that there is insertion at position 1, which is T. T was inserted in the target strand and it's not present in the input. And we say also A is inserted at position 2 here. and it's not present actually at the input. So, and we also see that the T and A is also extra in the target and it's not present in the input. That's why we say that it is an insertion. Okay, and if you look here, okay, so the best, this input and this target actually exactly match. So we will, the matching index is at 0, so they stop matching because they are equal, so they're matching from here. And the best similarity, because they are also matching, so you find your best similarity score is 1. No mutation is fine because they are exactly matching, so there is no changes, no addition, no deletion. Okay, and again, you're able to see again, if the input is smaller than the output, like in this case, so you will see that you will notice that we have starting from 0. Okay, so the best alignment is from 0. Okay, and this is the best matching position, and of course GG does not match anything here. And then we put the TA like that, TA. Okay, and we would say that at GG, DG have it, they got GG in the target strand, but we don't have it in the input. So we say that there is insertion at position 3 and 4. So the last 2 position, I'm sorry, having matching. Sorry, I apologize. So, totally sorry. So this is an insertion at G. G and G, position 3 and 4. I apologize. Seems that I'm losing focus. Okay. So let me try to go to the code and try to explain that before I start to lose my my focus here. Let me go here. Okay, and let me remove this. So that will take some time, but let's hope that we are able to do it fast. Okay, so this is the length. We have seen that before. This is the best index. We also have seen something similar before. Now I would like you to understand something, that we actually are going to always the target, the input must be bigger than the input length must be bigger than the target length. If this happens, so we need to call, because again, the best strand match can only really work if the input is really bigger than the target. So can you notice here, we did not pass input strand here, we actually switched. So if the target length is bigger than the input, and this sometimes happen in this specific case, so we pass the target as if it is the input, just to find the best match. So we just need to find which position, which index is the best match. If we have -1, I mean, sorry, I apologize. This if statement is checking if the best index is not equal -1. So if it is not equal -1, it means that we managed to find something. Let me check again, because I'm starting to lose focus. We return -1 in which condition? Let me check here. So if we can remember, -1 is actually returned here, best strand. We return it -1 if the target length is bigger than the input, but this will never happen because we already switched the position here. So we switched the position in a way that we avoid, sorry, not here, here. We do this switching if the target length, and sometimes it is, so sometimes you find that your input is TA, and your target is like TAGG. I think we have seen that in the sample run. So this is the input and this is the target. So in this condition, the target is actually bigger than the input. So we have to then pass the target as if it is an input and start to find which is the best position for alignment, for aligning these two. Okay, and we of course based on the best score, so we will find that okay, the position 0 is the best place in their matching. T matched the T, A matched A at exactly this position. Okay, so now we start to add dashes to the smallest. So in the if condition that we need to perform in later, we need to actually add dashes here. We need to make the two we need to make these two how to say strings are exactly equal. If we are not able to make them equal, we are not able to detect if there is a deletion or if there is an insertion or something like that. So you cannot compare a character to nothing. So you have to put something that you can compare characters in. So if you put TA like that, so you will compare, and this you already insert dashes here. So you see here we insert the smallest. Okay, so we add dashes to the smallest, and if we know that the target is bigger, so we pass here the smallest strand, and we also pass it the target strand and the best index. Okay, so this will try to match where is the best matching position, and then we'll add slashes here. So what if the best so what, imagine that you have here A. So it means that, imagine here, I just want to give you an example that yes, it's true that this is input is smaller than the target, and then we find that the best matching index is 0, 1, 2, and so on. So if it is 0, 1, like that, it means that we are matching at position 1, the best matching here, best index at position 1. And so we, again, if we want to compare here and tell if this is a deletion or this is an insertion, we need to insert something here to compare it to A. Okay, so it means that we need to add a dash here. So that's why we need to pass the best index here. So this add dashes to the smallest. I will leave this explanation to the end. If not, I would like you to check it. And so this function actually just add dashes. It will match here and then start adding dashes before and after, so that both the input and target strand are having equal characters. Yes, but any missing character will be just added as a dash. So this is the result from this add dash. So now we will replace the input strand with a new strand. So that will be full of dashes like that. So this is exactly the input. And now we're having dashes before it and after it. And it matches exactly the same count. So here, 5 characters. We also here having 5 characters after this line. So what if you now imagine that the input is bigger than the target? So we will do just nothing. We will switch nothing. We will just get the best strand match. So you see the difference between here and here. We switch nothing. We just pass the input as if it is an input, and we get the best match, and we get the best index. We still add dashes, but we will add it in this case to the smallest. So inside this function, we will check which one is the smallest from in both of them. and in the smallest we will add dashes and we will assign it to the target. Here we was not assigning it to the target. Here we was having the input is less characters than the target. That's why we add dashes to the input and we store it in the input. Here we have the input bigger than the input. So maybe maybe you are having this your input, and maybe you have TA as your target strand. So typically you will add dashes here just to make this, sorry, apologize, to make them 4. So these 4 characters, we add dashes to make all of them is 4 characters, just in case that the input is bigger than the target. Okay, so this is exactly the same, and just be aware, when I got the length of the input here, I got it based on this. But when I change the input strand, I add dashes to it. So the length is actually become now different. So I need to update the length after I add the dashes. So my for loop works well. And the same goes here. If I add dashes to the target like this, I need to update the length also. Okay, I need to take the length after I added the dashes. And then let's have a look. So again, if my alignment return -1, if the best index is -1, okay, so I will just I say best alignment index is equal -1, and I will return nothing. Okay, so now again, where did I get my best alignment index? I'm getting my best alignment index up here, best index. I'm getting it here. I am printing it out here. He needs that exact string exactly the same. And also this should be exactly the same. Any addition or deletion from the spaces or any spelling mistakes, it will cause the canvas not to work. Just be aware of that. This is the biggest issues. Any small mistake here in the strings will make it not work. Okay. And also they need everything to be printed exactly the same way, that in the same arrangement here. Okay. So now, so this is the for loop where we are going to detect insertion and deletion and then substitution. So, okay. Let us try to put somehow, we assuming that this is, again, in this case, this is our input. This is our target. So our for loop are based on the input. So because we always assume that the input is actually it doesn't matter, because we make them the same size. So we add dashes to the input, or even in this case to the input, to make it actually equal to the target. So both the input and the target is the same length. So we just not, we want to execute from 0, 0, 1, 2, 3, 4. Okay, and this 4, so the count here, we have 5 characters. So the length is 5, but we are running from 0 to 4, because we're counting in programming, we're starting from 0 to count the indexes. Okay, so the point here that let me try to even do some press, just some spaces, so that this is a bit clearer. Even spaces here, maybe spaces here, maybe then off the AI. So okay, I would say okay. So this is enter, another enter. Okay, so what we are doing here, that in this we compare character by character. So here we are comparing the input strand to the target strand. Okay, and as we know that both of them is equal, and we managed to add dashes to the places where actually based on our alignment index. So we know that the best index is at 1 here. This is 1. Okay, we know that they are best matching at this position. So we add dashes before and after. So we start to compare A to dash. So when you compare A to dash, it means that this condition is satisfied. They are not equal. So if they are equal, we do nothing. So there is no substitution. There is no mutation. So it means that the DNA does not change. It is the same. Okay. But if there is a change, if they are not equal, so we need to go inside and start to detect: is it insertion? Is it a deletion? Is it a substitution? So if it is, if you see, I'm comparing to what? I'm comparing this. If the input is a dash, so it means that the target actually was having kind of insertion like that. So the target have something inserted. So typically we, if we look here, TA, I apologize because in the example, in the example that they give in the instruction book, they actually put the input on top. Okay, so okay, so if they say that the input is a dash, it means that the target have A inserted to it. Okay, so this is marking the input, and this is marking the target strand. And so if input equal dash, it means that A was inserted. So we will print out exactly the same string. If a single mistake happened, then it will not print correctly. And you notice, because at I position, when I equals 0, we start I equals 0. So when I equals 0, we will say position 0, but he doesn't want that. He wants to say that this position is actually, to human, is position 1. So human look does not count from 0. Human count from 1. So that's why he adds 1 here. Okay. So what we want to say that when dash in the input, there is something here. We said this is the insertion. What if the target have a dash? If the target have a dash, like in this case, for example, the target, let me see, no, if the target have a dash, so let me, if the target is the one that's having the dash, so if the target is here and the one it's having a dash here like that, let me assume, just for assumption, which is not in the case here, if it is having the dash, the target, it means that it having a deletion. So there was something here, it was deleted because it was available in the input and it is not there in the target, so it was deleted. Okay. In this case, we don't need to we don't need to do that. In this case, we don't have any deletion here at all. We have only insertions. Okay. And typically from what I have seen, that we either have deletion or insertion. Okay. So this is position 0, I equals 0. Let me go down and we talk about substitution. So substitution means that you will only see it. In this case, we don't have any substitution. So this is all insertions. But substitution will happen if, for example, so if this is U, for example, okay, so you compare A to U, okay, so it means that they are still not equal. And it means that, so the last thing that you're going to check with else, so you check first with if, and the else will actually check the target, if the target have a dash, okay, to mark a deletion. And the substitution is if this is not dash and this is not dash, okay, and they are still telling that they are not equal, it means that they are not matching. There is a character here that is different from here. Okay, so this is called substitution. So a substitution means that the character here and the character here is not it's not the same, and they are neither of them is dashes. Okay, so only then you will run, you come here. So this is what we talk about substitution. Let me see, let me try to remember, when did we say that the count, we need to count actually? Yeah, so I make this count actually, I mean, when I try to run first at the start, I did not need to actually put this count variable at the bottom, which is this one. I needed to put it because I found that to be able to tell that there is no mutation found, I need to do some counting. So every time, so if you can see here, let me see. So do you see this? Let me see, where is that exactly? So if I put here, this is the end of this else, and yeah, so I am putting it here. Yeah, so this is if, yes, so this is a big if. So if, okay, if they are not matching, okay, they are not matching, that input character and the target character not matching, so we will do this, we execute that. If then they are actually matching, so if t is equal to t, so I will start to count. If a is equal to a, I'll start to count. So at the end, if I am having an input like that, T A T A, and then I have the input as T A. So this is input strand, and this is the target strand, T A, also T A. So if they are both of them matching, it means that I compare character to character, and then I keep counting. Then I will count that 4 of them. I will. So every time he check that if they are not equal, actually they are equal, so this will not execute it at all. And then I will just add count. I will keep counting until I reach 4. So I will find that both the 4 are matching, and then I compare this count to the input length, and then if the 4 characters I have and my count is equal 4, it means that all the characters are equal in both the input and the target, and then I will just print no mutation is actually no mutation found. Okay, and that's it. It took so long time, but yeah, it's a slightly complicated one. I hope I explained it well.